Hello. So we've investigated the particle in an infinite well, and I told you that could be a model, for instance, the nucleus of an atom. Specifically, like if we had a proton or neutron trapped in an atom, it's going to have some quantized energy states, and we could use this as at least a first order approximation. And if that's the case, then we should be able to see some ramifications of that, like if what happens if a photon, or excuse me, if a proton decays from, say, the n=2 state to the n=1 state. That should give off a photon. That photon should have an energy equal to hc over lambda, uh, where lambda is the wavelength and E is the energy difference between n=2 and n=1. So in this case, what I'm going to do is I'm going to actually treat that using that same wave function, the energy that we found and everything. I'm going to actually compute the energies of the 5 lowest energy states of a proton in the actual nucleus of an atom. So I'm going to assume the length of the box, or the length of the well, is actually about the size of a nucleus of an atom, which is about 2 times 10 to the negative 15th meters. I'm going to assume the mass is the mass of the proton. And from that, I'm going to calculate the energy states for n=1, n=2, 3, 4, and 5. Then in part B, I'm going to actually calculate the energy difference between n=2 and n=1, set that to hc over lambda, so that I can find the actual wavelength of a photon that would be emitted. If that's the case, if this is fairly accurate, then we should get a ballpark figure of what kind of energy comes off of a nucleus when it spontaneously does what we call gamma decay. In fact, there's a couple types of decay of a nucleus. There's a beta decay, where either a electron or a neutron, or excuse me, an electron or a positron is emitted. There's an alpha decay, where an alpha particle is emitted, and then there's beta decay, or excuse me, there's gamma decay, where just photons are emitted, and that seems to be the case when a neutron, or excuse me, when a nucleus is excited, so that the proton is in a higher energy state than it normally would be, or the neutron's in a higher energy state than it would normally be, and it drops down and gives off a photon of light. Well, we happen to know that when that happens, those photons are normally in the gamma ray portion of the spectrum. So they're on the order of wavelengths being 10 to the negative 15th meters. So let's calculate now those energy states, how much energy it is, and let's calculate the photon that would be given off from an exchange from n=2 to n=1 of a proton. So turn on my document cam. Okay, so here's everything drawn out. I've got the equations. I made use of the fact that, remember, when we actually solved this Schrodinger equation with u=0, we found that the Schrodinger equation is true for all x, provided that k is equal to the square root 2m times e over h squared, h bar squared. Remember, h bar is h over 2 pi. Then the boundary conditions required our ansatz solution, which was psi of x equals a sine kx plus b cosine kx. That required b equals 0. Then the other solution, the other boundary condition, psi of L equals 0, forced the k here to be equal to n pi over L. When I set this k equal to that k, that gives me the energy, and the energy is n squared h squared over 8ml squared. Of course, for n=1, you just get that. So I call that quantity h squared over 8ml squared. I call that E1. And we're going to calculate that, but it's basically 51.19 MeV, or 8.20 times 10 to the negative 12th joules. So we're going to use that. I'm going to calculate the energy of the 5 lowest states. That's n=1, 2, 3, 4, and 5. And I'm going to use the width equal to about 2.0 times 10 to the negative 15th meters, which is roughly the diameter of a nucleus. For part B, I'm going to calculate the wavelength emitted when a proton decays from the n=2 state to the n=1 state. In other words, I'm going to do E2 minus E1, set that equal to hc over lambda, solve for lambda. And I'm going to use this special version of h times c. It's the same one. It's 6.626 times 10 to the negative 34th times 3.0 times 10 to the 8th meters per second for the speed of light. But if I then convert it, instead of joules times seconds, or excuse me, joules times meters, if I convert that instead to electron volts times Newton meters, I get this quantity, and that's a lot easier to work with. So let us start. First off, I'm going to calculate what E1 is. So E1, which is defined to be n squared for n=1, so times h squared over 8 ml squared. And of course, for E1, this is just 1. So I get 6.626 times 10 to the negative 34th joule seconds squared over 8 times the mass of the proton is 1.673 times 10 to the negative 27th kilograms. And then the L is 2.00 times 10 to the negative 15th meters. And basically it goes from 1.76 for helium, for hydrogen, to about 11 or 12 for uranium, the more or less largest nucleus. So this is a fairly reasonable result. Of course, I got to remember to square that. When I actually did that, I put in those numbers. I've got 8.20 times 10 to the negative 12th joules. And of course, if you divide that by 1.602 times 10 to the negative 19th, and I actually divided that to more sig figs so that I could actually keep the 4 sig figs, I get 51.19 MeV. So that's the energy of E1. Okay. Now, since the energy goes like N squared times E1, we can then say E2 is equal to 2 squared times E1, which is 4 times 51.19 MeV. Of course, that turns out to be 204.8 MeV. E3, which is 3 squared times E1, which is 9 times 51.19 MeV, mega electron volts. That turns out to be 460.7 MeV. E4 is equal to 4 squared times E1, which is 16 times 51.19 MeV, which gives me 819.1 MeV. And finally, the last one we're asked for, this is all part A, by the way, is E5 is equal to 5 squared E1, which is 25 times 51.19 MeV. And in this case, it actually bumps all the way up to 1.280 GeV. In other words, we get 1,280 MeV, and that's, of course, 1.280 GeV. So we now have the energies that were asked for. Now, if we wish to actually calculate the energy difference between E2 and E1, actually I should have included that in the box as well. If I wish to calculate the energy difference, or in other words, the photon wavelength that's being given off, what I realize is that the lambda of a photon that's given off due to the proton going from 2 to 1 is actually equal to hc over the energy from going from n equals 2 to n equal 1. So that's hc over E2 minus E1. That's really how we calculate it. Now, hc, I told you, was 1,240 eV times nanometers, and nanometers, remember, is 10 to the negative 9th. I'm going to divide that by 204.8 minus 51.19, and this is MeV, so it's times 10 to the 6th EV. So that gives me electron volts, so that'll cancel out with that. So this will automatically give me energy, or excuse me, wavelength in nanometers. And nanometers is really small, but lo and behold, when you divide 1,240 by this, you get 8.072 times 10 to the negative 6 nanometers. Well, a nanometer is 10 to the negative 9th, so 10 to the negative 6 times 10 to the negative 9th would be 10 to the negative 15th. So it's 8.072 times 10 to the negative 15th meters, which is exactly what I'd advertised. I told you that we know that gamma decays from the nucleus tend to be wavelengths on the order of 10 to the negative 15th meters, which are in the gamma part of the spectrum. And lo and behold, we got a gamma ray photon, which we can also write as a wavelength of 8.072 femto-meters, because the femto is 10 to the negative 15th meters. So not only does this infinite square well give us a neat idea about quantization, it gives us a wave function, it actually gives us a realistic model of the nucleus of the atom, in the sense that it predicts that the nucleus of the atom, if protons or neutrons change energy states within the nucleus, then it should put out photons on the order of 10 to the negative 15th meters in wavelength. And that's exactly what we found in the experimental situation. So if you look, for instance, at Dirac's book on nuclear physics, where he was developing during the Manhattan Project, you'll see that femto-meter photons were the norm coming from the nucleus. So I think that's a really good introduction to the use of the infinite square well. And I think that should help everybody better understand how quantum mechanics, even when these simple models, can be applied